All right, folks, it's Bass Action back in action here. In this top box on this page, I'm going to summarize some of our exponent and logarithm rules, keeping in mind that logarithms and exponentials are just inverses of each other. So they just work backwards and forwards. We're going to summarize these rules, and then we're going to practice some more complicated condensing. But the real important element of these rules is going to really come into play when we start solving our logarithmic equations. So just a quick review, log base a of 1 is 0. This is going to be super important when we start graphing. Log base a of a is 1. We've been using that one quite a bit for just simplifying logarithms. And then this is similar to the exponentials that we've been working with, two exponentials with the same base. The exponents are equal. Same idea, two logarithms with the same base that are equal, then their arguments are equal to each other. So we can say that m equals n. Now, the next three logarithms, I have some proofs written for these three on the next two videos. So you could spend some time just watching those, maybe even on a higher speed, just to get an idea of why these work so you're not just memorizing. Okay, so the first one here, we have r times log base a of m. And the key here is to see that we have this coefficient in front of the logarithm. So one option, and I emphasize that it's an option because you won't always want to do it, especially when you're solving, but one option is to take that coefficient and we can write it up top as an exponent. So this would be written as log base a of m to the r. That's going to help us when we try to condense and sometimes when we're solving. The next thing is that two logs, same base, that are being added, what we can do is we can take the arguments and we can multiply them when we write it as a single logarithm. So we'll have our log base a, and then we'll have an m times an n. Of course, if that one makes sense to you, the next one really will. Again, two logs, same base, this time they're subtracted. So if we multiplied when they were being added, we're going to divide when they're being subtracted. So we will have our log base a of m over n. So let's just jump into some examples here. Now these are going to be more complicated than what we'll encounter when we're solving, but these are just good skills for us to be familiar with. So the first thing that I want to look at on example A is to recognize that I have two natural logs, which means their bases are the same. They are being subtracted, so I'm going to be able to divide these two arguments, and the arguments being this and this. And then the other thing that I want to recognize is that I have this coefficient of a 2 specifically on that logarithm. So I'm going to write myself a note that this is going to move up top. This is kind of some good stuff to take a look at in the beginning so that you don't have to do quite so much rewriting each time. So when we go to write this as a single log, I can do a lot in my first step. So I'm going to say natural log. I'm going to take the first argument of x squared plus 3x plus a 2. I'm going to put it in the numerator. I'm going to take the second argument and the exponent of the 2 and put it in the denominator. And what I'm going to do is I'm going to write it as an x plus 1 times an x plus 1. That's going to be a little more helpful for me when I go to simplify. Now the next thing that I want to do is I want to start looking at this whole actual argument. Are there things here that could simplify? So what I'm going to do is I'm going to factor that numerator, and you always want to be looking for opportunities to factor in these cases. So I'm going to have an x plus 2 and an x plus 1, and that's over my x plus 1 and my x plus 1. So now I can see that some things are going to cancel. I can cancel out some of these x plus 1s. So my final answer then is going to be the natural log of x plus 2 over an x plus 1. And that's my final answer. It's very important to remember that you only write the log itself one time. All right, so let's take a look at my next one. What do I have going on here? On the next one, again, I have two logs. They're both base 10 this time. They're being subtracted, and I have a coefficient. So I'm going to write myself a couple notes. My coefficient is going to move up top. I can also take a look at this argument right here, and I can recognize that that's going to simplify. That's going to be a 25 minus a 1. So I can just immediately in my mind start thinking of that as a 24 instead. Again, we want to try to simplify some of the things that we're trying to have to write every single time. So I'm going to have a log, and in the numerator, since my logs are being subtracted, I'm going to put this 8 to the 2/3 power. And then in the denominator, I'm going to put my 24. Then I'm going to start to clean up that 8 to the 2/3. So thinking back to our algebra 2, I want to write that 8. Okay, I want to write this 8 with this base of 3. So what I'm going to do is I'm going to write log, and I'm going to write 2 cubed, and that's still to the 2/3 power, and that's still over 24. And now I can see that those are going to cancel. So what I'm going to end up with is log, and I'm going to have a 4 in the numerator now and a 24 in the denominator. So my final answer is log of 1/6. So sometimes students get worried, hey, how am I going to get from this log 1/6 all the way back to that original? And just know that's not a question I'm going to ask. There's tons of ways that we could get, expand a 1/6, but I just want you to be able to show me that you can simplify and condense all of that. All right, my last example here is a very, very crucial example, and it's very significant for us because we have 3 logs, or actually, sorry, in this case, I made it 4 logs, and specifically, I have a double negative here, and that's going to be really important and how we handle that. So what we want to think is like we did really basic rules of our order of operations, and we just want to work left to right and just slowly condense. So we're going to grab the first 2 logarithms first, and I'm going to rewrite that one initially as a natural log, and I'm going to multiply these 2 arguments. So I'm going to have my 9, I like to put the 9 in the front, and the x squared plus a 1. And then I'm going to rewrite the remaining 2 logs, natural log x minus natural log 5. Now I'm going to take the 2 leftmost ones, and I'm going to condense those. And now this one is going to be a division, so I'm going to have my single log of natural log. The numerator is the 9 times the x squared plus 1. The denominator is just an x, and I still have a natural log of 5. Now I can simplify, and this is where we're going to go back to that idea that I've talked about a lot, that instead of writing a fraction divided by something, we want to think this fraction times the reciprocal of that. That's going to make your life so much easier. So what we're going to do here is we'll write natural log, and we'll have our 9 and our x squared plus 1. You could distribute the 9 if you wanted, times a 1/5. So our final answer is natural log 9 times x squared plus 1 over a 5x. That's going to be our final answer there. So it's very, very important to remember that, especially when you have that double negative, that's kind of your red flag on that you need to multiply by the reciprocal. All right, that's all that I've got here. You could just on a higher speed watch those other 2 videos, and then we're going to get into our solving.